chemistry students. So today, what we're going to be talking about again is redox reactions. And I want to actually show you some of them and show how we can actually use these things. So we're going to start with some zinc nitrate. So we've got some zinc nitrate in this container. Now, if we just take a piece of zinc and you put it into zinc nitrate, you wouldn't expect anything to happen because remember, this is just solid zinc. It's got an oxidation number of 0. And here we have zinc ions that are +2, but there's no reason why the zinc would become +2. There's no reason for any type of reaction to happen. What about if instead of zinc, we use a piece of copper? So this has to do with how active it is. This is copper with an oxidation number of 0. Will it change and become copper ions when I put it in zinc ions? Does copper that's 0 want to oxidize in zinc that's ions? Does it want to reduce? Does that happen when you put copper in zinc? Do you see anything happening? No, that doesn't really happen. Copper is lower on table J. Copper is less reactive. There's no reason it would oxidize. However, if instead of using zinc ions, I use copper ions, any blue solution, chemistry is probably going to have copper ions in it, transition elements. So here's our copper ions. Now, if I take a piece of copper that has no charge, here's our copper ions that are +2. I put that in there. That shouldn't do anything. That's not going to react at all. But if I take my piece of zinc, now look what happens. This is no charge. This has little charges of +2, and these want to reduce, these want to oxidize in the presence of each other. So if I put zinc and copper, that's going to make a reaction. Now that's cool and all, but what's actually happening is the electrons are leaving the zinc. There's 2 electrons that are leaving the zinc, and they're being absorbed by our copper ions. Is there a way that we could use that energy? Electrons moving, that's electricity. Is there a way that we could actually capture that? And it turns out there is. In order to do that, you're going to make an electrochemical cell, and this is what we're going to talk about this week. You need 2 solutions. So I've got my zinc ions, my copper ions. You need 2 electrodes, zinc and copper. Now when I put them in here, notice I'm not putting them this way. If I put them in here, then this one would react. I want to spread out the reaction. So I'm going to put them in here, so they're not going to react. This is just zinc and zinc ions and copper ions. And what I need to do is connect these. If I give a way for the electrons to flow, then they will flow. Give it a wire for it. Now this isn't enough. You need something else when you're making an electrochemical cell. And that thing you need is a salt bridge. It's a way for the ions to transfer back and forth. So to do that, all we're going to do is take a piece of paper towel, get it a little bit wet, and we're going to provide a bridge for the charges to go through. So here's my bridge. It's just a wet paper towel. I'm going to put it in each side. So now if we let it sit and saturate a little bit, if I now allow a place for the electrons to leave the zinc, it's higher on table J, so I'm going to let the electrons leave the zinc. There's a solution down here. And the electrons are going to travel through the wire and come over into this wire, and they actually will start to oxidize over here. Okay, the reduction is going to occur on this side, and you actually will start to see the reaction happen. It's super slow, and it's very difficult for you to see what's happening, and how do you even know if there's electricity in here? It's not going to it's not enough to give me a shock of any kind. So in order to see if this is actually working, what you're going to use is a meter, a little voltmeter, and what we're going to do is attach one side to the positive and one side to the negative. And you should see the meter start to read. So it doesn't work. We're not getting any voltage. Our electrons aren't flowing from here to here, and I think I know why. This is what a standard salt bridge looks like, but we have a really porous bridge between our 2 anode and cathodes, so I don't think it's allowing for the ions to transfer, which is the real problem. So instead, we're going to use this type of a porous cup. So instead of using this salt bridge, let me get the meter out of the way. We're going to pour our solution into our porous cup. And into that, I'm going to put the copper. Now, hopefully, when I set this into here, look at that. It's amazing Look at all the electricity that we're getting. Look at that. It's amazing. It's not working at all. But this is the idea. There's something going on. Let me see if I can fix it. Got it! I just had the wires backwards. Of course, if the copper is being reduced and the zinc is being oxidized, then oxidation occurs at the anode, and in this case, that's going to be negative. So the ands are going to be negative. So that's the black one. It needs to be on the negative. That's going to be on the negative. And then the thing that's reduced, the cathode, is going to be positive. So to go over these, in order to make an electrochemical cell, you need 2 electrodes, you need 2 solutions, you need a salt bridge, and you need to realize whichever one's higher on table J is going to be oxidized. So in this case, it's the zinc is higher on table J. That's going to be oxidized. That's going to be the anode. So that's the one that's going to be negative. Ands are negative. The cathode, on the other hand, sadly, the cathode starts with cat. That's going to be positive. So when you attach it, we're getting almost 0.75 volts, which isn't bad for a couple of liquids. Attach a bunch of these and I'd have a battery. Wait, I have a battery now. Huh. I'll see you on Thursday at 3 o'clock, where we talk about electrochemical cells and table J.